I don't have a very long talk today. I'm just going to speak about the work we've done with Sri Sharan, Sridan, and Chris Maron over the last few months or a year, and it's basically using a model, very simple model that we now extended to a finite element model to simulate the seismic cycle into a fault zone of finite thickness. And the idea here was to basically model, laboratory experiments, basically validate the model with laboratory experiments. Okay, so the way it's coming, basically, it's coming from this. I'm not really, or now I am, but for the longest time, I'm a person who worked on large scale deformation using dynamic relaxation methods, explicit method into elastoplastic media. So it has a lot to do with the approach I used after, you're going to see, and to simulate that fault zone of finite thickness. The model I'm going to show is this the 1D approximation or the 1D formulation, but it's also kind of the beginning of trying to have a more consistent with laboratory experiments and geological observation models of the seismic cycle. So this is the kind of stuff we're doing for longest time, being able to do large-scale deformation in finite element mesh with dynamic remeshing and able to do very large deformation using, explicit methods. And over the last few years, the explicit methods have become very, very popular, and dynamic relaxation methods have become again popular. So in this case, we're just looking at a fault zone of finite thickness, and the idea is really from these pictures from Kirkpatrick, which is an observation in the field, basically, is can we model a fault zone of finite thickness as is observed in the field, with this complexity here where you have, zones of fractures, CS, localization, zones which are either plastic or viscous in between the zones of localization and deformation where slip may occur. So the first step that was to come up with just a model that's supposed to take into account the thickness of these shear zones, okay? And there's one kind of a justification in the lab for that is the work by Maron and Kilgore in 1993, which shows that there is some scaling between the frictional weakening distance Ds of C and the thickness of the shear zone here. So it's linked, basically the Ds of C is actually linked to the shear strain, but it also linked to the gouge layer thickness or the fault zone thickness here in this picture. Ds of C is scaling somehow with the gouge thickness. So beside the observation in the field, there is some justification to look at that in the lab and trying to use the lab as a first step to get into what we observe in the field, okay? So the experiments in the lab were done by Sri Sharan, and Chris Maron. And that's the panel on the left here, the very simple experiment. There is a fixed support, a quartz gouge, I will give you more details after. And deformation is driven by a plate, so this is driven simply, by two rigid blocks, okay? And here, the model is basically very similar. The choices inside the models are choices have been made over time, okay, to match what's happening into the quartz gouge, okay, the slip that we observe, the stress drop and everything in the quartz gouge, okay. So the moving plate here is moving at the same as this bottom plate here, okay. There is normal stress applied to the model as well, and there's a fixed place at bottom, and what it is basically the moving plate is dragging, multiple kind of small frictional interface linked by a viscous damper, a dampening, system here. So basically the damper are usually the same as the radiation damping that's used in seismic cycle rate state formulation. Okay. So so the loading stiffness is calculated differently from the response of the different interfaces here. So here is basically the formulation. It's very simple, okay? The implementation was a little bit more difficult, but the idea is very simple. Basically, the shear traction on the interface for the rate and state blocks, you know, for all these small interfaces is equal to the loading history, the loading from the upper plate, basically some rate and state loading, elastic loading, basically the difference between how fast the plate is driven on top and the slip velocity generated by the rate and state interface, basically, and then the radiation damping here. And it's really made in two steps, you know. One step is to calculate the loading history. Basically very simple. I mean, I will show that again, you know, basically. And the other step is to adjust basically both the loading, this difference in strain rate, which is dependent on the thickness of the shear zone here, dependent to adjust it as a function of the loading. So there's two steps. Step one, we calculate the loading, and this is done with dynamic relaxation method. The step two is to adjust the velocity to respond to this loading, and, you know, to readjust the strain rate between the upper plate and the frictional interface, if you want. So here we have the numerical model. So I just repeat that, you know. So we have normal stress. Step one is loading these springs, you know, and the step two is to adjust, you know, the frictional interface and the radiation damping to respond to this loading. Okay, and we're gonna repeat that it's an explicit method, so it's a 1D rate and state method. So we use an adaptive time stepping method for Lapusta and Liu. But since we also trying to use this dynamic relaxation method to calculate the elastic part, we have to use this you know, inertial damping, and also this you know, fictitious mass to actually match the quasi-dynamic, or sometimes we can also have the fully dynamic simulation. Okay. The rate and state, you know, the part where we adjust the velocity in the frictional part of the model is actually using basically Lapusta and Liu 2000, 2009, using the same parameterization, the same time stepping and everything. So it's very consistent with the rate and state formulation that's used in the community. So here is the explicit formulation, starting from velocity, you know, at 1 point slip velocity at the interface. We calculate the shear traction stress on the fault zone, so the loading on the fault zone, basically. And we use then the FLAC, or the dynamic relaxation method, to calculate the change in loading history. We apply that then to the fault zone using Lapusta and Liu, you know, something also that was done in 2017, to actually get the velocity, you know, using Newton-Raphson method. Okay. And then explicitly we return every time step to that. So this is very simple, okay? And actually this didn't take very long to develop, actually. And it's a MATLAB code. It's been published once. We're republishing it now with Sharon and Chris, basically. But basically has, you know, lots of variability in the behavior. You know, what's expected, we try to do, you know, this W over H star scaling, like in the, you know, the Rice and Liu paper. We get some somewhat different behavior. We use it to simulate, you know, a normal fault between two, you know, very simple ways, you know, of doing that. And we find very, you know, consistent behavior with rate and state. So the next step is that one, you know, can we use that model that is able to take into account some thickness H of the shear zone and all the other properties of the rate and state models to actually simulate, you know, a real fold gouge or fold zone of finite thickness. So the first step of that was to actually use a lab experiment that was done by Srisharan and Chris at Penn State years ago, and to see if using the exact same parameter as the lab experiments, could the numerical model, you know, behave in the same way. And these experiments on the fold gouge, so the lab and model setup, the fold gouge was basically 5 by 5 centimeters square. We cut a slice through it in the model, numerical model. The fold gouge thickness was 3 millimeters. You know, the particle size, the quartz grains, basically they're 10 micrometers. The rates of deformation, so they vary the rates of deformation. They correspond mostly to things that looks like slow slip events, okay, or tremor or LFEs, you know, basically. So, and then, you know, the corresponding Ds of C is 2 micrometer. You can calculate a nucleation length, you know, from that. The shear modulus G is 200 megapascal, and the effective stress on the fold gouge was 21 megapascal. And the, you know, the calculated B minus A for the rating state 0.004. The state variable is calculated using the same as, you know, the Lapusta and Liu model, and so it's kind of working pretty well. So what you see on the top left panel is in purple are the laboratory experiments for different rates of deformation. So the 13 micrometers per second and the 4 micrometers second. So, and then the bottom one is what the model was able to do. Okay, so it's also 3 millimeters fold gouge, you know, it has all the same properties. And you can see that there is a very good match between this behavior, you know, aperiodic behavior for different rates of deformation that's observed both in the friction experiments and the numerical model. So you have the same, it's just one part of it. The models basically fold average shear stress here here as a function of time. In the model is measured inside, you know, the fold zone. For the lab experiments, it's actually measured, you know, above, you know, in one of the rigid blocks. So the shear stress will look different. I will show you other results that, you know, basically show a result for one point inside the model instead of taking the average of all the different points in the model, okay, for all these little asperities if you want. But we match pretty well the period, the long period and the short period of the frictional behavior. It also, in terms of sleep duration versus sleep duration between fold average stress drop, so we kind of match, you know, it's not perfect, obviously, but we have, you know, a good match. We're in the same domain as the lab experiments. So we decided basically to look at, you know, more details inside the model. Okay, so we look at the space-time evolution of slow rupture. So they're driven at, you know, this 13 micrometers per second or 4 micrometers per second. And, you know, this is a numerical model of the lab experiment, if you want. So what you see in the top panel is confined or partially confined ruptures. So you see this rupture propagating, you know, this deep purple zones where you see this rupture propagating in one direction on some length scales inside the fold zone. That's small, okay? The event migration over time, they migrate around at 0.1 to 1 millimeters per second in the numerical experiments, okay? And the estimated critical nucleation length, so the H star or LC, as of C, is about 4.8 millimeters. This is smaller than the size of the shear fold zone. So basically the fold zone is 5 centimeters. And we have, you know, the critical length about 4.8 millimeter. This may be seen at your confined rupture even in small scale samples. So it looks like we have a very complex behavior already at the you know, in a numerical model that kind of correspond to what you expect in the lab experiments. The bottom panel is just, you know, basically if you want profiles over time of the slip velocity across you know, this different, this upper panel. So the blue dot correspond to the blue profile, you know, clear blue dot here correspond to the profile, and then yellow, here's the profile. And what you see is the numerical model at each point shows this kind of aperiodic and also kind of sometimes chaotic behavior that's that correspond very well to the lab experiment. Okay, so we show a periodicity in chaos into the numerical experiment, like in the model. So it was very successful. I mean, in some sense, very successful. So we decided to use this numerical model, basically very simple approach for a full gauge, basically to actually ask this question: can we use this model validation, put between quote, okay, to scale up the fold gauge thickness and explore the behavior of nested fold gouges in the thicker fold zone? Okay, so the idea is to see, you know, if we can reproduce this kind of behavior, which is, you know, kind of pushed by this observation in the lab, that D's of C can scale with the thickness of fold gauge. Okay, all right. Also, the observation, the geological observation of the complexity, the fact that you have, you know, a thick shear zone inside it, thinner shear zone, even thinner and shorter shear zone. So this kind of scaling, kind of nested fold zones going into, so the first fold zone would be several meter thick, and then you go into meter to centimeters to millimeter thick shear zone. And the strain rate on each more and more localized shear zone would be higher and higher. So can we kind of reproduce this kind of nested behavior? We made a picture of what it would look like, you know, on a very simple. So each one of these, at the bottom right panel here, each one correspond to a very thick shear zone, and inside you have a blue shear zone that is, you know, kind of thinner, and then you go to the orange shear zone and then the red shear zone, and you can go on and on and on towards more and more localized deformation. And for each of these shear zone will be driven by the strain rate of the larger shear zone, making it this nested system of shear zone that works. So the larger one has a very low rate, and when you localize on the low rate of deformation, when you localize on the thinner and thinner, you get higher and higher rates of deformation. And so this is what we did. So this is basically the idea. So here would be a 5 kilometer wide and 1.5 kilometer thick fold zone. And this is a very, very large thing, okay, in that case, okay? And to get this kind of deterministic, this is the idea, and to get this kind of deterministic chaos and aperiodic behavior that looks like SSCs, okay, we need to have a D's of C in that case of 20 millimeter, keeping all parameter constant. So the only parameters here to scale up every time is D's of C, okay? And we know that, you know, from lab experiment, D's of C is scaled with H, okay? It's true for the lab, and, you know, so basically we both, you know, in the numerical model, we then, you know, both scale D's of C and H, okay? And, you know, to make it simpler, we use H star or L of C, L's of C, you know, the nucleation length instead of D's of C to scale up. Okay, that's the same because we L's of C, H star contains all the rate and state parameters. Okay, so this is the result. Okay, this is presented here, model nested fold gouges. This is presented in terms of these plots here on the left side. Characteristic duration versus seismic moment, okay? And each one of these kind of clusters of dots, you know, gray to red, orange, clear blue, and darker blue, okay, correspond to different numerical experiment where we scale up D's of C and the shear zone width and thickness, okay? So the larger shear zone is all the way on top in dark blue, would be the one I just showed you, you know, D's of C 20 millimeters, 5 kilometer thick fold length, and 1.5 kilometer thick fold zone. And the driving velocity is 10 to the minus 9 meters per second, okay? So you see that we get this, you know, aperiodic behavior, slow slip over years, you know, kind of time scales here. And then as you go down, you know, the driving rate must increase, obviously, because we have thinner and thinner shear zones. and we scale down D's of C with and the thickness of shear zone, and so we go from 2 millimeters D's of C, 200 micrometers, 20 micrometers, 2 micrometers. The lab experiments are here in gray, okay, and they are just like you know, that's basically the same as the lab experiments. They're down there. They will be, you know, in the range of duration and moment, you know, so that would be, so we'd have to scale it up, you know, because we have only a line. So to scale up the moment, we have to do some you know, calculation of some surface area. But basically, it scales up with LFEs, you know, and then as you go up, you know, you scale up with VLF, you know, very low frequency earthquakes, and then you go up to SSEs and silent earthquake as you go up into the system, basically. So this kind of this nested idea, the top one driving smaller one, you know, seems to scale fine, you know, if we take the lab from the lab experiments up to the numerical model and scale up into the numerical model, okay? The interesting thing that come out of this simple, very, you know, in my view, it's a kind of a simple model, but basically what we see is that for each of these clusters of dots, basically we have done scaling, and we see that the duration of these events is scaling with as cube, you know, as a cube of the magnitude scales as a cube of duration. So it's they all like each one of these clusters behave like earthquakes, okay? Which kind of makes sense because basically it's a nucleation. We nucleate an earthquake, but you know, we have all these other properties that seems to be kind of you know, making it slower in this scaling, okay? So and then there we looked at other kind of source properties of rupture in the numerical models. Basically, this A and B, we look at the average slip and rupture length versus characteristic duration. What we find that with increasing characteristic duration, we show a linear relationship between these quantities, okay? So there's really a linear relationship between, you know, characteristic duration, rupture length, and average slip. The rupture velocity has no apparent dependence on moment for a given numerical model. So here, the average rupture velocity, you know, is the interesting part is that we get up to, you know, the meters per second when we go up to the smaller ruptures, okay? The smaller the rupture, you know, the faster the rates of deformation, which would correspond to LFEs and all these things, you know, even though we are doing it in the quasi-dynamic sense, this is still making a lot of sense for this scaling, okay? And then finally, the average stress drops on all these events is very, you know, similar across. Basically, it's order of basically tens or 100 kPas. So we're kind of happy with that. So we put together a unifying framework. Basically, that's mostly Sharon's idea. It's kind of putting all these things together in a you know, framework for this fault zone of containing nested other shear zone or fault zone that would work together, you know, so the larger shear zone would drive the smaller one and stuff like that. So it seems like, so putting the load, so all these figures kind of complicated. You have the critical nucleation length on top, you know, the bottom you have the critical slip distance D's of C, the fault length, okay? And one line across is a line across our model. Basically, this is going from the faster rates, the LFEs in this red dot, going up to VLFEs, and then, you know, up to slow slip events in this chaotic and aperiodic behavior that we have here. And you can change the path. Basically, you can take other paths where you decrease the rate, and this path is like this three, you know, a pass free, a pathway free. The pathway one is the one that we model, you know, it's basically nested zone. But if you go along that path, you get, you know, pathway free, you have a more dynamic behavior, you know, your rates should increase faster. So the fault zone should behave more dynamically. And so what we see when we do these experiments, we see that we can get, you know, in that path, we can get earthquakes, basically. They're not kind of yet because it's just a 1D model. The rupture propagation is not yet, like a crack rupture, at the shear wave velocity, but we're working on that in a 2D model right now. And then if you choose pass 2, you go, toward the pass where you get more, less dynamic events and more silent earthquake and stuff like that. So in conclusion for this part, basically, we produce slow earthquakes mode on a quasi-dynamic fault zone model that explicitly incorporates information about fault thickness. So we're successful at that, okay. The other part is the model is able to well reproduce frictional complexities observed in laboratory stick slip experiments, including aperiodicity and chaos, which I think is the biggest deal here that I don't, spend a lot of time, but basically it's kind of surprising that this simple, physics model is able to get us this kind of behavior. And we simulate a suite of models where elevated slip rates during slow motion events in one model is used to drive loading in smaller models. So this is this nested fault zone kind of idea. And, scaling the D's of C, okay, with shear zone thickness and maturity in this framework produces a spectrum of slip mode for seismic creep and to slow and fast rupture. So this is what been, we presented that to the community. Sharon did several talks and stuff like that, and now we submitted a paper on that. Do I have more time or?
I think you've only used 26 minutes
And I
so
have
far, so you should have a little while.
I have only 30 minutes, no?
Yes, so another 4.
4 minutes. Okay, so basically, we have developed other approaches to simulate, stick slip behavior and fault zone in these long-term models. One of them, is also to look more at, so one of the idea in this kind of figure of the fault zone is that there be both brittle rate and state and ductile behavior inside the fault zone, at some depths, materials at any depths anyway. Fault zone can behave ductily, and brittly at the same time. So that was one of the things we developed, several years ago. We're still working on it, but as in the previous model, the state behavior, the rate and state behavior was really consistent with the empirical observation in the lab and, what's been done over the years for this kind of slow slip events and earthquakes, but in that case, we use the more Coulomb formulation. The same, I'm going to go fast damping formulation, and we try to actually simulate the state behavior. So I'm going to skip quite a few things. We use more Coulomb theory. We try to simulate the state behavior by the weakening. We assume that we reach a yield stress like in more Coulomb, and the corresponding weakening or strengthening in the more Coulomb space, correspond to the rate and state behavior. So we serve both rate and state and more Coulomb. And, so I mean, in details, it's more complicated than that, but basically what we really want here is both the velocity weakening behavior that decrease friction or increase friction and the state behavior, which is simulated somehow, it's not exactly the same way, but simulated by the loss, the dissipation of energy through plasticity, okay, into the more Coulomb phenomena. And we were able to simulate earthquake. So this is a picture from several years ago, 2018. And we had the same behavior, we have a lot of similar behavior as rate and state. We're able to re-simulate the same experiments as, the lab experiments to get the same, both the direct effect and the evolving effect of the rate and state. And we use that to simulate, so we have these elements that are brittle and these elements that are viscous into a shear zone, and try to simulate mixed brittle ductile behavior in this very complex shear zone. And basically, what we found is that in this very complex, because there's both this kind of brittle behavior or weakening and strengthening behavior of a fault zone or a rate and state shear zone, and the ductile behavior, we obtain shear zone. We can have both, can have as in the same kind of cycle, slow slip event earthquakes, or a creep for basically different ratio of brittle versus ductile behavior. Basically, that was the idea, and we analyzed the patterns of deformation to see how they match the observations. This is very different from the previous Mars. You know, we have no. I don't right now. I haven't been able to take the Moore Coulomb behavior and to really match both state and rate behavior of the rate and state. You know, the empirical view of it. So if I would take one of these models and try to do the same thing as before, I wouldn't be able to get this kind of aperiodic and chaotic behavior like in the fold zone that I modeled in the previous part of the talk. Okay, so, and you know, that's basically the goal of all that, is that to take this 1D model that I did, you know, for the rate and state, this very successful, you know, validation with lab experiments, and to simulate that into a 3D, into you know, another code, and basically try to see if we can get this kind of complex behavior more explicitly of nested fold zones and brittle ductile behavior into a fold zone. Okay, I think that's basically it for today.